to you about deciphering Buruli Ulcer disease dynamics, the power of mathematical modeling. And before I even go any further, I'm very glad to attend my first Black Heroes of Mathematics conference, and later on this is my first talk since I finished my Viva. So I'm very excited. And I'll tell you a little bit about my background, and then I'll tell you part of my research part of the research I've done in the past couple of years. So I come from Africa, particularly from East Africa. And as you can see, this part of Africa is where I come from. And particularly I come from a very beautiful country in East Africa called Uganda. And in Uganda, I come from a very small town called Lyantonde, which is in the south central Uganda. And the time when I was growing up, it had a population of around 7,500 people. That's where I did my primary school. And this is a picture of me and part of my relatives. I think I was around 7 or 8. And this is me transitioning from primary school, secondary school, and to university. I did my secondary school at a school called Trinity College, Kabali. And while there, I did physics, maths, economics, and entrepreneurship at my A levels. I think the equivalent of GCSE here. And I recall that in around when I was 17 or 16, my dream was to become a civil engineer, and particularly specialize in transport, construction of roads. And I always got fascinated with how you can rebuild a country by changing the transport system. And much as I didn't know the details of what it entailed, that's what I wanted to do at university. But when I finished my A levels, I wasn't given civil engineering. I was given Bachelor of Science with Education, and this was because I didn't have the cutoff points for civil engineering. For it had higher cutoff points compared to education. So I was admitted to Makerere University, which is the oldest and biggest university in Uganda. I did a Bachelor of Science with Education, and I was specializing in mathematics and economics. And this is a picture of me and my mom on my graduation after my undergrad. And after my undergrad, I worked as a teacher, a high school teacher, teaching mathematics, commerce, entrepreneurship, and economics. And one of the challenges that I faced as a teacher was that before you go on to payroll as a government teacher, you first of all first register as a teacher and then get on government payroll. But between when you register as a teacher and when you get on payroll, there's a period. And so I was in that period, there was poor pay, delayed salaries, and a very high workload. And I remember thinking that I needed to do something else to help me, live by, because I couldn't live by as a high school teacher then. So I had a conversation with a friend on Facebook who I had taught with at some point, and he encouraged me to apply to AIMS. And I remember very well in his words, he said that AIMS will show you how multifaceted maths is, and encouraged me to give it a try. He not only encouraged me, but he supported me through, read my essays, reviewed my application, gave me guidance on how to apply and everything with the AIMS application, because he had gone through the AIMS system before. So I did apply and I was admitted at AIMS Ghana, class of 2013, 2014. Also, I was in the same class with Angela Tabiri. And while at AIMS, I remember getting so fascinated with maths, with applications of maths, with a group of people that we were all from different African countries put together, and all we discussed is how we can change our countries, how we didn't know this, how the spectrum of applications of maths in industry, in modeling infectious diseases, in finance, and it fascinated me so much while at Ames. So I did my structured. So the system of Ames is that you do a structured masters, and you have modules, a little bit of everything, and then at the end you choose a project. So my project was in financial math, and again, it was more the joy of doing something, of seeing maths beyond algebra or geometry, but more of maths that I can explain to my grandmother in the village. So I did a project in financial maths, and then I took a short break, and I did another a research master's at AIM South Africa in mathematical ecology. You would wonder why I would come from finance and then ecology. But for me, it was more of exploring. I felt AIMS opened my mind to explore what maths can do. And the question that always ran in my mind is, how can we use maths to solve problems faced in our home countries? And this stemmed from the conversations we usually had after classes while at AIMS, where the problems that people faced from Western Africa were the same problems we faced in Eastern Africa, not any different from problems in North Africa. And I believed that maths would be the catalyst to problem solving, because this was reiterated to us as AIM students that we are the people to solve the problems that concern our countries, ranging from poverty to disease to the things we grew up seeing on a daily basis. So for that reason, I believe that a PhD would open my mind to new horizons, not only in research, but also exposure and diversity, to see how things are done in places beyond Africa, and to be able to translate that knowledge and skill set back home. So I was very grateful and privileged to get a PhD position at the University of Southampton, working with Professor Rebecca Hoyle and Professor Christine Curry and Professor Rebecca Simmons from the University of Surrey. And Professor Simmons is working in microbiology, so she gave us a problem in Buruli ulcers, which is her specialization, and wanted us to use maths to actually understand the dynamics of Buruli ulcers. So that's the reason why Buruli ulcers was chosen. But also, I realized it was more local or more common in sub-Saharan Africa, which is where I come from. So the question is, what is Buruli ulcers? Buruli ulcers is a chronic debilitating disease that affects the skin and soft tissues. And it's a neglected tropical disease in the same family as tuberculosis or leprosy. And it's caused by an infection by a bacteria called Mycobacterium ulcerans. Its mode of transmission into the skin is still unknown, and the highest cases occur in children below 15 years living in rural and tropical environments. Though it can affect people from different ages, but the highest cases are in children below 15. So this is just a map showing you where the cases have been. The highest cases have been in, you see in sub-Saharan Africa here, and we have more cases in West Africa, followed by Central Africa, and some cases in East Africa. And shows you the cases up to 2015. Not very updated, but it can give you an idea of how the distribution of the disease. There are also very high cases in Australia and some in the Americas. But generally, the disease is not very common. And this is how it manifests in the skin. So World Health Organization categorized the manifestation of the disease in like category 1, category 2, and category 3. So in a layman's language, you get a boil on your skin that is painless, that grows over time, and in weeks, it spreads through and become deep ulcers. So people go to hospital when it's late stages, and because it's painless, and this is how it manifests. This is a cross-section view of Buruli ulcer in the skin. And this is, imagine this is your skin. This is how it would be. This is a nodule. And then after a few weeks, it will break through deep down into the subcutaneous tissue, and it will have undermined edges. So surgery becomes tricky because the disease has curves in. So treatment can be tricky, and the bacteria lies at the edge of the lesion. The motivation of the study is that Buruli ulcer itself is a health challenge in remote areas in some countries in sub-Saharan Africa, like we've seen, and it's a poorly understood disease that has emerged since the 1890s, given the fact that the mode of transmission is still not yet known. So that tells you how much more research is needed to study Buruli ulcers. When someone has contracted Buruli ulcers, it takes a long period to get healed. So it involves some surgery, skin grafting. The costs of this surgical treatment are high, and you will spend a lot of time in hospital. So then also the late diagnosis leads to delay in seeking treatment, partly because the early symptoms of the disease are painless, so people seek treatment late. Also, the physiological processes that lead to observed features in Buruli ulcers are still unclear, and this will be the emphasis of my talk. This part is what I will focus on. So I'll explain the skin cell death mechanisms. This is now the processes behind the manifestation of the disease. So the bacteria, when Mycobacterium ulcerans enters the skin, it secretes a toxin called mycolactin, which is responsible for ulceration. And the mycolactin can lead to cell death through mechanisms, direct and indirect. In the direct mechanism, when mycolactin is produced in the skin, it accumulates into the cytosol, which is part of a cell, and disrupts the proteins in that cell, leading to cell stress. Eventually, the cells die. Then the second mechanism, which is the indirect mechanism, when the mycolactin enters the skin, it disrupts the process of thrombomodulin, which is a protein responsible for blood clotting, and thrombomodulin and fibrin are responsible for blood clotting. And the presence of mycolactin disrupts this, and they end up being depleted in the skin. And this leads to ischemia. Ischemia is lack of oxygen. So there's oxygen transportation in the cell is disrupted, causing to cell death. So the model that we are working on, it's we developed a mathematical model that describes the dynamics of Mycobacterium ulcerans growth, the mycolactin diffusion, and the decrease in cell densities in the skin as time evolves. And we also explored the processes that lead to cell death caused by mycolactin diffusion in the skin. We also investigate how ulcers progress due to ischemia and direct toxicity pathways, plus their contribution to ulcer formation. And then we also examine the speed of the enlargement of the wounds. So these are some of the processes we included in our model. The bacteria cell growth, which we model the movement of bacteria and mycolactin are modeled as diffusion processes. And we model this using Fick's law of diffusion. So this term here, it comes from the Fick's law. And bacterial cell growth is proportional to bacteria cell density. And this was limited from growing exponentially in time at a rate Ku, and lambda u is a constant birth rate. So this term here, which we use as a logistic growth, when you remember when you're modeling population dynamics, we believe that there's a time where there will not be enough resources. We limit the resources so that the model doesn't go just exponentially in time. So this gives us this equation, which is illustrated here. Then the mycolactin diffusion is produced. Mycolactin is produced by bacterial cells at a rate lambda m, and diffuses into the skin at the diffusion with a diffusion rate dm and decays into this at a rate km. So this, because bacteria produces mycolacton, these equations almost look the same. They're not the same, but they look the same. There's a diffusion and then the production and then limiting it to from being exponential. And then we have the skin cell distribution. So we assume the skin is made up of the endothelial cells and the stromal cells. And both types of cells are sensitive to mycolacton. And we assume that they're specially mixed with a uniform just with a uniform 9-1, which means that the stromal cells are 9 and then the endothelial cells are 1. And when cells die, no new cells grow within the time of ulceration. This assumption is based on the fact that the presence of mycolacton disrupts immune cells, and so the skin can't fight back the infection. Then for the skin cell death, direct contact of mycolacton with the skin leads to cell death. And this skin cell death is proportional to the skin cell density if the local concentration of mycolacton exceeds the threshold, which we call C, and I is either endothelial cells or stromal cells. And this gives us our equation as this, where H is the heaviside function and D is a death rate for the two types of cells. We use a heaviside function because when M is less than C, then we have 0. When M is greater than C, it's 1. So it's like a switch on, switch off, which is perfect for a heaviside step function. And then for the cell death by ischemia, cell death by direct toxicity, when the mycolacton concentration is above the endothelial cell threshold, fibrin accumulates in the capillaries, causing interrupted blood supply, leading to ischemia. So this again is a heaviside function, and then this is the cell death by ischemia, and this is the type of cell. So these are the two equations for the two types of cells, the endothelial cell and the stromal cell. And so we non-dimensionalize the equations and establish the boundary conditions and initial conditions. And also we establish the model parameters and values and the sources used. Then we solve the equations numerically in Python using ODET function. And these are some of our results. So this is the bacteria cell density. This is the mycolacton concentration. And bacteria, so in the places where it's blue, almost 0, that's health skin. And at that place, we believe that M is less than C. So the mycolacton levels are still low to cause cell death. Also, the bacteria is still very low, but it hasn't produced enough mycolacton. And we use this, and the initial infection was a very small Gaussian infection to start with. And that we observe that U and M, U being bacteria, M being mycolacton, multiplies logarithmically until it reaches a plateau. And we stop the simulation before U reaches the edges to avoid edge effects. And our equation for bacteria resembles a Fisher-KPP equation, which has a traveling wave solution. A Fisher-KPP equation is an equation that has a diffusion equation and logistic growth, which is what our U equation looks like. So the traveling wave solution, the two traveling waves both start at 15 and they extend to both sides, to the left and to the right. And this actually tells us how the lesion spread out on an entire domain, and this being given the different time frames up to 106. Then when we come to the death of skin cells in response to direct toxicity and mycolacton and ischemia, here we put the two mechanisms together. And then we observe how the cells die. So you can see, you may not notice the difference, but I will make the comparison and you can be able to see the difference. But the idea is that this is an endothelial cell, this is a stromal cell, this is just 0.001 and this is 0.009. So there are more stromal cells than endothelial cells, and how they reduce over time. So we see a significant reduction in cell densities, and also again, the cell density is at 0.09 when M is less than C. And now we observe the joint and individual effect of ischemia or direct toxicity. So at this particular plot is when both are together. And then I make a comparison. I make a, oh, sure. Then here I want to observe how the wounds form, the speed of wound formation, how the wound extends from the center, which center was around 15 back. So we pick one side and then we look at how the wound spreads out. And we obtain the speed of the wound by calculating the slope of this graph. And this helps us to know how fast the wound is forming and and the decrease in the cell density. So when you compare mechanisms here, in these plots, we have the two mechanisms, the joint, the direct toxicity and ischemia. Then we have direct toxicity alone, and then we have ischemia alone. And then we give M an equilibrium, just a value slightly above the stromal cell threshold, and just a value above the endothelial cells threshold. And then we want to see what effects this is. The changes may not be very observed, but you can see the green here, which green is at 15, and yellow is at 12. So we see the first drop is at 15, the first drop is at 12, the first drop is at 15, and the first drop is at 12. And the same here for ischemia alone. We see the first drop here is at 12, and the first drop here is at 15 days. So from those plots, we can conclude that the earliest drop of endothelial cell density for the three cases happens at 12 days, when the mycolacton equilibrium is at 1.5 times 10 power negative 7 grams per mil. And that happens, it's highest when both ischemia and direct toxicity operate at the same time. And the key feature to observe in these results is how changes in mycolacton relatives to skin cell toxicity thresholds can influence the process of cell death observed in Buruli ulcers. And then these results affirm what is already known on how high amounts of mycolacton combined with the type of skin cell can speed up the cell death. So in conclusion, the model is fundamental to Buruli ulcer disease, providing more understanding on how the lesions form. For example, we're able to switch the two mechanisms on and off, which is difficult to do experimentally, if at all possible. And wound enlargement depends mostly on the ratio of the diffusion coefficients. This was because of the alpha. Alpha is a ratio of diffusion of mycolacton to the diffusion of bacteria. Our results echo the role of mycolacton in influencing Buruli ulcers. Also, our results reflect that combining the two mechanisms leads to a quicker cell death than individual mechanisms. When analyzed independently, skin cell death through ischemia was more rapid than through direct toxicity. And the key limitation of our study was lack of literature and data for parameter estimation. And also, there was unavailable experimental data was unavailable, and this posed a challenge for model verification. So we suggest if we can, and this is a bit of a problem when working with diseases that are common in countries where data isn't very available. So if we can collect data on, for example, on parameters that influence these diseases, this would really be helpful for improving the model, and also data for model verification. So the contribution of this model was that it's an addition to available literature providing more understanding on Buruli disease ulcer formation. And our model shed light on the importance of considering treatment of late stage wounds as a key strategy in BU control and management. So most of the work has, for interventions and strategies for reducing Buruli ulcer, we're actually not looking at reducing, we're looking at elimination. So most of the strategies did overlooked the treatment of late stage wounds. It looked more into avoiding, into increasing diagnosis, increasing early treatment. And those are really important for Buruli ulcers, but also it's important that when someone has already got the disease, what can be done? So also we can use this model to suggest the type of data that should be collected as research on Buruli ulcers evolves. So this work also guides clinicians and researchers to make predictions about skin tissue degradation caused by Mycobacterium ulcerans. And here, because of the nature of the disease in the skin, I think knowing how far the tissue is degraded would be instrumental for surgeons. And so, yes, this knowledge is important in assessing wounds recession margins, which is key in Buruli ulcer treatment. And finally, our results will be important in making informed decisions on surgical excision during surgery. And these are my supervisors just minutes after I had done my viva. So I'm very thankful to them and thank you so much for listening to me.